Yeah, this is actually coming from a paper that I wrote during my day as a support engineer at MTR, where I was mainly studying transformer health, and I was responsible for doing a bunch of online monitoring of like how high voltage equipment, for example, for transformers, high voltage cables, high voltage switch gear, and so on. And I didn't really like plan to do this presentation. It was really in the last meetup where like Henry just sat next to me, and then he said, "Well, hello, my name's Henry." And then I was like, "Okay, hello, my name's Philip." And then he said, "So, would you like to be the host of the next meetup?" And I was like, "Is that how you greet people?" Yeah. And then and here I am like doing this presentation. Okay. So this presentation is gonna be a little bit technical. I think Ethan just said that his talk about like Python and sport is very niche. This would be like the forefront of the research, and I don't really expect you to like understand everything here because it's really technical. And even for like electrical engineers, not all of them are doing DGA, but I will try to like put it in a very layman manner. And I think the takeaway from this talk is that how we can use machine learning in different applications rather than like putting in this specific application. So there will be 4 parts. The first part I will talk about transformers and DGA, and the second part is what DGA analysis we've been doing, what are the current technologies or the technical understanding of DGA. And the third part I will like dive into the details about the machine learning models I did. And the fourth part is a little bit more qualitative, is about like my thoughts about after doing all these much. So can I have a show of hand who's ever studied electrical engineering or physics in high school, and you have like a general understanding of what a transformer is? Okay. Okay, that's not bad. Okay. Who's ever like trained a machine learning model before? Oh, okay. I think more people study physics. Okay, so a little bit background of what a power transformer is. In a typical electrical network, the power goes from the generator to the household. Okay, and in this whole process, we will go through transmission, and it is usually more efficient to step up the voltage to very high voltages before stepping it down into our household. So in Hong Kong, we use like 220 volts, right? And then in the US, we use 110 volts. But along the way from CLP or HKE, we use very high voltages from the generator. And then it comes to MTR at 132 kV. And then we step it down to 33 kV. And then further step it down to 11 kV. And finally 415. So any ideas, any thoughts about why the end voltage is 415 instead of 220? I thought some people study physics. Yeah?
Well, maybe your devices would explode.
Partly. And why is that? This is a historical reason.
Because
British standard.
Exactly. Give him a round of applause. So I actually have some souvenir for you. Thank you.
Thank you.
I still have one more. Okay, so the British standard was 240 instead of 220 we use nowadays. And since the MTR, the urban lines are built in the British states, so the typical voltage used at the stations are 240. And because that is like the phase voltage, if you count the line voltage, that would be 415. So if we zoom into one of the transformer here, In a transformer, we have the primary side and the secondary side. The primary side is a higher voltage, and the secondary side is a lower voltage. That is a step-down transformer. And if we put this into a more mechanical view, what's in the transformer, apart from the coils, the core, we also have the transformer oil here. And this is the part where much of the maintenance, much of the focus we have here today is how the transformer oil behave inside a transformer. And actually, by analyzing the behavior of the transformer oil, we can deduce the health of a transformer. So we don't have to like open the cover of the transformer and then peek into it and to see if there's any defects or any burn marks into it. But we can just by analyzing the oil, we can extract a fraction of the oil, and then by analyzing it in a laboratory, and then we can just deduce how is it going inside the transformer. And because there is a thermal and electrical stress inside the transformer, thermal stress meaning that it's operating under very high temperatures. Electrical stress, if there's any electrical fault, like a sparkling, like a partial discharge, it will try to release a bunch of strong electrical energy into the oil and break down the oil into some gases. And that's what we say there are decomposed gases in the oil. And the gases will be dissolved into the oil. And so we have the name dissolved gas. So this is what a transformer looks like in reality. And if we open the transformer, it will be like this. And that's why we do DGA, because we can't inspect this transformer all day long, right? And this is actually happening in a laboratory in Hungary. So it is a factory test. We can't do this in Hong Kong. We don't have this much space. We can't have a crane as big as that doing inside a station, and that's why we need DGA. Okay, summary, this is a oil type transformer. We also have like air type transformer and some other type of transformers. It's step up and step down AC voltages, and there are thermal and electrical stress inside a transformer. And of course, if you pull out the core, it will look something like this, and the oil is like that. So transformer oil, it acts as an insulating medium between the live part, which is the core, which is the thing that we just pull up, and the shell. The shell of the transformer is, the shell, the container that contains the core, and it operates under high temperature. Usually in Hong Kong is about like 60 to 70 degrees. I will talk about that in the later slides. And it serves as a medium of cooling because when you pass the electricity into the coils, into the copper, there will be copper loss. There will be heat dissipated from the transformer, and by circulating the oils, the cold oil, and then by circulating air into the we call that the wings of the transformer. In Chinese, it's like 盖液 of the transformer, and then we can bring the heat away from the transformer. And also it provides the arc quenching capabilities because, as I said, when the electrical sparks appears inside the transformer, it's going to absorb some of that energy and decompose the oil into some gases. And there are in various types. In MTR, mainly there are mineral oil, silicon oil, and synthetic ester. So this is the key part, DGA. We extract some of the oil typically every year. In some certain cases, we might do that half yearly because we might want to see the trend of the gas generated. And it is a part of diagnostic techniques that we use to somehow to deduce the health of the transformer. It's not a necessary thing to do. It does not, so as to say, it is not a sufficient evidence of any fault inside a transformer. Neither is the contrary the truth. If there are any faults in a transformer, it may not reflect into the gas content. So this is why it's a little bit difficult to apply DGA directly, because there are so many things that can happen that may not be captured easily. In some IEC standards, there are typically like 13 or even more key gases, but in most analysis, in my analysis, we only use a few of them. And in the machine learning model that I will talk about, I use 7 of them. But so as to know that there are many gases. So they are hydrogen, methane, ethane, ethylene, acetylene. These are the key gases. In Chinese, that would be 氫氣、甲烷、乙烷、乙烯、乙炔，係啦。咁methane 就即係沼氣啦，跟住乙炔就係嗰啲電石氣嘅，即係焊接嗰啲咁樣。咁所以呢啲都係易燃氣體嚟嘅。咁其實喺 lab 嗰度做都有啲危險。It's a little bit dangerous to do these kind of analysis in a laboratory because they are all very explosive gases and basically toxic gases. So we will receive a laboratory report like this, and then just by seeing like the results, the numbers, and they are typically in ppm, which means part per million. And we can see, for example, in a small bottle of oil, we see 13 ppm of hydrogen gas and less than 500 ppm of oxygen. So in a lab report, we will see some, like by IEC standards, the fault code is T1, which means it is a thermal fault, which means the transformer is so hot and we need to do something about it, or something worse might happen. But is that the case? It's not the case, because this one is confidential, but this one is from a certain distribution transformer in the island side. If this transformer fail, like maybe half of the stations in the island side will get an outage, and so far we don't see any case like that. So is this laboratory report not, can we trust this, basically? So it talks about IC 60599. It gives us an interpretation table like this, and we have to like do some maths, and then there are some ratios, and then there are many considerations. Actually, the standard is quite poorly written, and it's difficult to do the diagnosis, to be honest. How difficult it is? The first thing is that it's not very convenient to do the diagnosis directly, because there is no universally accepted approach to do DGA. IEC standard is one thing, but if you go to the American standard, we call that the IEEE standard. They have another set of rules or approach of interpretation. So which one should you rely on? And also, if you look at the title of these technical standards, it all says guide, which means that they are guiding you to do something. This is a huge disclaimer. You can't rely on it. You have to make your own interpretation, your own application, how to adapt your transformer in your company. And the third thing is that all of these standards are based on studies or research of large transformers, which are like high voltages, ultra high voltages, like 33 kV to 11 kV. Actually, even higher than that. But in many of the small transformers in Hong Kong, we usually do with 11 kV to 415 volts. So does these standards applicable, are they applicable to some smaller transformers? Also, another question is, these standards are developed in UK and in the USA. Are they applicable to the climate in Hong Kong, to the loading we have, and to this specific network configuration we have? These are the questions that remain unsolved. Also, so as an engineer, I receive like lab reports, and then it tells me, okay, this value 10, is it safe or not safe? That's the decision I have to make. So what value or what threshold do I have to use in order to determine what's safe and not safe? Okay, so and then I go to the IEC standard, right? Okay, and then by this part you will understand why it's so poorly written, so poorly like phrased. So the typical value, it doesn't really say a safe value because that's a disclaimer, okay? It's just typical, it's not safe value. And the typical value is the gas concentration normally found that have no symptoms of failure and that are exceeded by an arbitrary percentage of higher gas contents. What do you mean by that? So what it says is that if your fleet of transformer, the top 10% has this value, then you can decide an arbitrary percentage above that. And then by those values, you will decide as unhealthy. That's what it tries to say essentially. But I mean, like, applying this wording is very difficult already. And to do some exploratory data analysis, I try to plot them, and you can see that this data set has its own like particular kind of characteristics. It's very skewed, meaning that most of the values are very small. That's normal, that's good, right? But some values are very big. It can come up to like 10,000 and 100,000 ppms. And they are still safe. So how can we apply this directly to machine learning models? If you've done something like this, you will know that it's very hard because the range of the values can matter the optimization process. And it's also very leptokurtic. It's a very high level word. It means that it had fat tails. So the values you can see on the chart on the right hand side, there are extreme values in the high side and in the low side. It's not easy to deal with these kind of data distribution. And also heteroscedasticity, which means that standard deviation is not stable. Okay, these are very statistical things that not necessarily need to know what's going on, but it's good to know, right? And that's why if you are using traditional models like linear regression, they don't really make sense because you can't they just don't behave well under these kind of assumptions or backgrounds. And I try to use some percentile like standard deviations and then to decide like what's the Six Sigma, right? If you deal with industrial process, we are used to the term like Six Sigma, but it doesn't really apply here. Also, the gas value are very sensitive to the environment. And if we look at the plots here, you can see there are many overlapping points, which means that the healthy data, the faulty data, they share very similar characteristics. And it is very difficult to interpret what's going on there. So with all that said, I try to develop some machine learning models, hoping that this approach would be something that can be helpful to us. But it's not easy, simply because in developing the machine learning models, I would say the most difficult part is how you formulate the question. For model building, later you will see it's actually much more simpler than that, especially with ChatGPT. The more difficult part is how you phrase the question, how you phrase your need, and what do you want to do with it. The first question I have here is, what does it mean to have a healthy transformer? So the oil in the transformer will decompose and will start to generate gas as soon as the transformer is energized. So the gas in a transformer doesn't necessarily fall into healthy and not healthy, but it appears in a spectrum of healthiness. like it is on the verge of unhealthy, but it's still healthy. Okay, so how can I like make sense of that? Second, we have very little data to train our model. You just saw that lab report, right? So I will need like thousands of those reports, and then to feed them into a machine learning model and to train them. I did that all manually, like putting PDF numbers into an Excel file. That would take time. So a better way to do it is to use some like sensors, online monitoring sensors, make use of like big data, but that would cost a lot as well. And it's very difficult to ask for this big amount of money from a public company. So oversampling, I forgot what I want to say about oversampling. Okay, all right. So when we're training the models, when we're training supervised model, we need some healthy data and some faulty data. Unfortunately, most of the transformers in MTR are very healthy, so don't worry about that. But it also means that we have very, very little faulty data. So how can we do that? There's a technique called oversampling, but compared to healthy data, we still need a lot of faulty data. And oversampling might do wonders. It might work, it might not work. We will see later. Also, like the fourth point, as I said, I manually input all that data into an Excel file. So it was a tedious task. The data is skewed. As I said, we see some skewness, heteroscedasticity, and fat tails. We need to clean them. We need to do some transformation to make the data more applicable, make the machine learning model works better. So here are the tests that are used. Anyone want to guess what are they? Yes, please.
Pandas.
Uh-huh.
Looks like scalar.
This one is the easiest, right? Yeah, the usual stuff. Pandas, scikit-learn, matplotlib, and ChatGPT. I would say using ChatGPT, knowing how to use ChatGPT well is ever more important because, well, you know the reason. That's why I said building the model per se is not really the most difficult part, because when you get the questions correct, you can do it quite easily. But how you make interpretations out of it is another matter. So in my project, there are 5 stages. So understand the problem. So my problem is we have a bunch of data given. We have healthy data, unhealthy data serve as a reference. So now I have one new oil sample and I did the lab test and the results are given. Is it a healthy or a faulty data? So we will try to understand it from the flowchart. Is a supervised learning because we have some data given as a reference. And it's also a classification problem because we are classifying it into health and fault data. It's not regression because it's not continuous class, it's a discrete class. So after you get the problem done, the remaining is actually quite easy. It just requires one line of code. So of course, there are many assumptions made. You have to understand what you are doing. But in essence, there aren't many, it isn't really that difficult. And that's why I really encourage you to try using scikit-learn or just to try to apply machine learning in your day-to-day task. So after getting the training data, of course, you have to clean it. and then you would like split it into train set and test set, and then if necessary, you would like do some transformation in the train set, and then you will need the validation set as well. And all of that should only happen in a train set. When you complete the train test split, don't look at the test set, because you might discover something in your test set, and then you modify your training procedures to make it fit better into the test set, and that would just sabotage everything. Why did I say that? That's because I've read many research papers doing exactly the same thing. They mix up train test and test set, and that's why they give very good results. But if you look at their code very in fine details, you will see that not many people follow this good practice, let's say. And then we prepare the data. This is a plot of how the healthy data and the faulty data would look like. I said I use 7 gases, so I can only plot it in 7 dimensions. We can see that it's actually plausible to do so, because we can somehow like slip a plane into it and then just decide which of the gases are healthy and which of them are unhealthy. And then we have to do something called feature scaling. Why is it needed? That's because in the first hand, we don't have beautiful charts like this. They looks. Do I have? Okay, I don't have the chart that's before the transformation. Given the wide range of the data here, it doesn't really show up on the chart that nicely. So this one is already done after the transformation. So there are several customary ways to do it. The first way is to use a z-score transformation or just normalization, but that won't work pretty. Like, that's what you can see. Okay, so that's also what most researchers did, and then they somehow managed to get the model work, and I just can't quite fathom how. And the second method, you do a log transform and then you apply normalization, and it will give better results like that. Okay, so our goal is to make the data more Gaussian, more normal, so that we can during the optimization, it would just behave better. But one thing about using log transform is that the data has to be non-zero. So in our case, it is not the best idea to use log transformation. That's because log 0 is undefined. And what some people did was they would add 1 into the data so that the whole data shifted 1 to the right. But I would say that that's not preferable, because we do have 0 ppms in our data set. And actually 0 and 1 does matter. For some key gases like acetylene, this is a very stable gas. And if you see 1 ppm in acetylene, that would mean something critical. So I would try to avoid that little step, adding 1 into it. So at last, I opt for a transformation called Yo-Johnson transformation. We don't need to add 1 into it, but it also gives us a very nice looking result. And that's why I use the Yo-Johnson one. The maths is actually quite difficult. All you need to know that it reduces. Okay, so the goal. Okay, so what the paper says is like this. So we have something called the Kullback-Leibler information number. It measures the difference of 2 distributions. And then after some mathematical techniques, they come up with this formula. And then what this formula does is that it minimizes one set of data or one distribution and a normal distribution. you can take a look at that paper if you're interested. And then, okay, so the fourth step is to try out different models. So after doing the feature scaling, you can actually directly apply some model onto it, and just to see what would happen. Okay, and then we can already see that some model would do pretty good. Like I would say SVC does pretty well, and also neural network, okay, fine. The lean one, the poly one, they doesn't really look good, right? And random forest, it looks good. And by doing all these like exploratory steps, you can already get a firm understanding of what your data would look like from a machine perspective. And then after training the model, you would evaluate it. You would see how well your model do. So it is an art rather than exact science. There is no textbook that teach you directly what metric you should use to evaluate your models. Some scholars use accuracy, which basically is a formula that correct predictions versus over all of the predictions. But one thing to note is that if your dataset is hugely imbalanced, that will create some problem, because let's say your data is 95% positive and 5% negative. Then if you only say it's positive, then the model will be right for 95% of the time. So accuracy, you will be extra careful about it. And what I opt to use is to use F1 score. It is a nice balance between precision and recall. If you're interested, you should read the documentation about how they calculate it. Also, one line of code. So after you pick one metric, and then you can see the cross-validation results, and this is how the model did. So what to note here is that if you see like the straight line over there, that would mean that the model does nothing. It's not better than a random guess. So the top performing models would be the curves that goes towards the corners. So I would say the yellow ones and the gray ones, and yeah, actually they did pretty good. All of them did pretty good. But at the end, I after some trial, after like putting them on different data sets, I would conclude that SVC and random forest did the best. Does anyone know what SVC stands for? Ah, okay, nice. Another gift. Okay, so the F1 score, 90 something, 80 something. That's where we would stop in most machine learning tutorials or books, because like 90%, 80 something, they all look pretty good. So the finding of this experiment, I skip a lot of things actually. I hide a bunch of slides because of the time limit. But some takeaways is that in DGA, in this specific project, we don't really need to use oversampling or undersampling techniques. They really doesn't show any difference in the result. And one big note is that always do train test splitting, or train set and test set splitting, and never look at the test set again until the very end of your training process. Because data leakage will happen, you will just accidentally leak some of the information from the test set to the training part. And you will it's best to avoid that. And after some trials, the YJ transformation works better than log transformation. To be honest, I think it's also okay to do log transformation. The metric at the end doesn't really show up that much of a difference. But I would avoid that +1 small action if I can choose. And after all of the experiments, I would conclude that SVC, support vector machine or support vector classifier, and random forest, they all perform better than the others. So the last part of this presentation is something that we all can think about. So I think this part is actually more valuable than all I just talked about, because with ChatGPT you can always build your architecture quite easily, but how to formulate the right question, that's the most difficult part. And these are just some random notes I wrote after I completed the project, and then sadly I left MTR, and then I don't have time to consolidate my thoughts. But it's happy that I have a chance to share to all of you. So the intention of this project is to enable something called predictive maintenance. Basically, it means that when I receive the lab report, I will be able to predict whether that transformer is at risk of failure. And that's because we can save costs. We don't have to wait for it to fail to develop faults, and then we arrange some emergency teams to carry out maintenance on it. But to be honest, it is a very, very big topic, and all I did was not enough to do it. It is because this model just gives you numbers. It doesn't give you any interpretation. Okay, when I feed one lab report into the ML model, it gives you healthy. What does it say? What does it mean healthy? If the transformer faults the second date, okay, I can take this as a learning, and then I will fine tune the model. Is that enough? In engineering, it's not enough, because we cannot afford the cost of that little failure or the missing predictions. In statistics, we would call that minimizing type 1 error, type 2 error. But in machine learning, most of the time, when we are doing side projects, or even in some very professional vendor-provided models, they will still give you some errors. They will still give you some missing cases. They will also give you a bunch of false alarms. And to us, to an engineer, these are really big problems, because we cannot make these kind of mistakes, and we cannot afford to make these kind of mistakes, because one mistake would really cost a lot. It would cost millions of dollars. Second, data collection. So we do have some online monitoring sensors in some of the transformers. We have some of them in Admiralty stations, some of them in Python stations. Installing them is already a big problem, because you might have some malpractice, not malpractice, but they just didn't install it in the best way, so that the sensors might get some glitches, and then you will often see some weird charts, some weird data, and then you will have to troubleshoot and do some calibrations, and it's not easy to get a perfect result. And after working for about 2 to 3 years at MTR, even I actively try to improve these sensors to make good data pipelines. There are still many glitches, many faults in those sensors. And also network reception is another thing. Many of the substations are buried into the ground. They are in the back of house of a station. They don't have good reception, and it's often the case that we don't see data for months, and then suddenly all the data come burgeoning in, and that's a very normal thing to see. And maintenance. So if I'm to to make predictive maintenance of a transformer. And now you give me this sensor, and I will have to carry out extra maintenance on this sensor. Is it cost effective? In the case of Hong Kong, it is not, completely not. Because we have so few vendors in Hong Kong and so few clients in Hong Kong that specialize in high voltage equipment, most of the projects, I would say, are very pioneering, but they are not successful in general. And all I talked about was the gases, and the dataset I use for the faulty data are from the IEC TC10. It is a technical committee that study DGA gases, but most of the research they do are on the transformers in the West. Majority are in the US and Europe. I would say that the climate in Hong Kong is quite different from that in Europe and the USA, and that also affects a lot on the result. As I said, the gas will decompose in under thermal stress and electrical stress. Technically, the mechanism is pyrolysis, and pyrolysis will only happen at very high temperature, and they are like 100 or something temperature. But in Hong Kong, the gas would pass out fairly easily, like in 70 or 80 degrees. So the behavior is quite different. And the last thing I want to talk about is that my manager once asked me this question: explain why you think this data is faulty data. And that will come to the fourth point, is that in engineering, we are used to principle-based thoughts. But in data science, in machine learning, we are using a data-driven solution, which means that we are using statistical tools that say something with some confidence. We have p-values, we have a kappa, but we don't quite understand the whole picture. We just understand how the phenomenon is and how we can improve it. But in engineering, we mostly follow principles. We follow Newton's law, we follow electromagnetic field theories, and it is not easy to persuade people from the engineering schools or they are well trained in engineering discipline into a statistical mindset. And so it's, I would say that it's a long way to go, but it's also a good result that we can discover more. Yeah, and many of the details you can find in this paper. If you search like HKIE machine learning soft gas analysis, you will come to this paper because it's the only paper in Hong Kong so far to do some research in this issue. Yeah. And that will conclude my talk. Thank you very much. Yeah. If there are any questions,
Yeah.
Yes, please.
I have a question. On the slide where you try to visualize the boundaries breaking healthy and unhealthy cases, do you have a sense why this boundary has such a strange shape? Does it really make sense? I mean, from your engineering experience, does it make sense physically? Or
That's a very good question. I think after the transformation, it would divide into nicely two big cluster looking. But if before the transformation, that would look fairly different. We can see there are a bunch of very small values in green and a very scattered value in red. I think it's a transformation that did what we see here and the question you made.
so basically, you mean that it was due to the pre-processing transformation, not due to the classifier itself?
I would say it's the magnitude that matters. Yeah, it's the order of magnitude, because if you do the log transform, you will see the same. So I think it's an order of magnitude that matters.
Okay, thanks.
Yeah. But a good question, thank you.
Yeah, last one, I think. Why you run publish the paper that your company is supporting paper?
So did my company supported this paper? I just raised this as like as an encouragement for other researchers, because it's a very niche topic, and even if you look for online monitoring sensors for DGA, there are only like a couple of them in the world that do this, and this project, I started it on my own because I have all these data and I think I can make some sense out of it. My manager didn't know this until I wanted to like submit the paper to HKIE, and then by then he understood, oh, you are doing this all alone in your office. Yeah, we can do this after in the networking section. Okay, I think we have to wrap this up. Yeah, thank you so much.
Yeah, so because we are running out of time, so I think like Philip can actually answer your questions outside, and yeah. So let me also just round up today's event. So very important.